Hi, welcome to this revision guide on the binomial expansion. I've got the index here where it will show you exactly the various sections that I cover, and also you'll notice there's time values, so if you want to check anything out, just go to that time on the video and you can then watch the various sections. I'd also like to mention that if you go to the description below this video, you'll notice that I've got links to exam questions based on the various topics that I cover, and also links to other associated tutorials. So do take a look at that and good luck. Now you may be asked to expand brackets like this: 1 plus x to the power 7, 2 minus 3x to the power 9, or 4x plus 3y to the power 6. They all have one particular form, and that form is a plus b all to the power n, where n is a positive integer. Now if you were to expand these, it's going to be a lot of work, unless you happen to know of a quick method, a quick formula. And that's what I'm going to be showing you in this next section. So we're going to be looking then at expanding brackets of the form a plus b to the power n, where n is a positive integer. And in order to generate some formula or pattern, I'm going to look at these basic expansions of a plus b to the power n, starting with a plus b to the power 0. Well, anything to the power 0 is always 1, so that's easy. When it comes to a plus b to the power 1, well, that's just going to be a plus b. For a plus b all squared, then you're going to need to start to write down your brackets, a plus b times a plus b in this case. And if you expand the brackets, you end up with a squared plus 2ab plus b squared. So we'll put that answer in. Now for a plus b all cubed, we're going to need to do a plus b times a plus b all squared. We've got the result for a plus b all squared, and when you expand it all out, you get this result. So we'll put that one in. Now finally, a plus b to the power 4, if you were going to do that one, then you can see it really is starting to get a lot of work, okay? So the result then anyway is highlighted here, so we'll just pop that one in. Now looking at these results that we've got here, should be able to start seeing a pattern. I can see that if we look at, say, the powers of a, and we'll take a plus b to the power 4, can you see it starts as a to the power 4, then goes down to a cubed, then a squared, a to the power 1, not that I've written the 1 here, and on this last term you could argue it's a to the power 0. Anything to the power 0 is 1. Keeping that idea in place, you can see it works for a plus b all cubed, a squared, a to the power 1, a to the power 0. And it does on a plus b all squared. Got a squared, a to the power 1, a to the power 0. And it's even true on these ones here. You've got a to the power 1, a to the power 0. And in this very trivial case, you've just got a to the power 0, which is 1. Okay, working with that idea, we can start to build up a formula. When we've got a plus b to the power n, we know that in every term it's going to go a to the power n, and it's going to go down in descending powers for a. So a to the power n minus 1, a to the power n minus 2, and so on, all the way down till we get to the last term, a to the power 0, which is effectively 1. Now let's have a look at the b's, starting with the expansion of a plus b to the power 4. I can see that the b's from this term here go upwards in ascending powers, b to the power 1, b squared, b cubed, b to the 4. Well, you could argue that the first one is b to the power 0, because that's going to be 1. b to the power 0, b to the power 1, b to the power 2, and so on, all the way up to our power here, which agrees with the power that we've got on the bracket here. And if you check it out for the cube one, you can see we could say we've got b to the power 0, which is 1, b to the power 1, b squared, and then b cubed. So if I look at this, I can add in that idea. So if I mark in the fact that in this first term here, it starts with a b to the 0, b to the power 1, b squared, b cubed, all the way up to b to the power n. The problem we have now, though, is what values do we put in front of each of these terms? We can see that they keep changing in each of these lines here. However, if I was to just mark those values in red, you can see that I've put a 1 in front of our terms that start at the beginning here, and I've also put 1s down here on the right hand side and highlighted in red the other numbers that we've got. These numbers form a particular pattern, and it's referred to as Pascal's triangle. So what is that pattern? Well, you can see then we've got all the ones coming down the side here, but when we want to find out what this value is, all we do is we just add these two ones together and it gives us the 2. If we add the 1 and 2 together, we get the 3 here. Add the 2 and 1 together, we get the 3 here. And you can see it carries on like this. 1 and 3 gives us the 4, 3 and 3 is the 6, and 3 and 1 is the 4. So by using this pattern here, we should be able to then put in our values into this formula. We know it will start with a 1 here and end with a 1. But using Pascal's triangle, we should be able to find out the values that we insert here where I've shown these question marks. And to show you how this works then, let's take this example, a plus b to the power 5. I need to figure out what the numbers are going to be in this expansion. We know there's going to be a 1 at the beginning and a 1 at the end, but we need to work out using Pascal's triangle what the next line would be. Well, following that pattern, it's going to turn out to be 1, 5, 10, 10, 5, 1. 1 and 4 makes the 5, 4 and 6 gives us the 10, 6 and 4 gives 10, 4 and 1 gives the 5. So we should be able to write in our values now. What I've got is the 1 from here. We start with a to the power 5 and we write in b to the power 0. The next term will be starting with a 5. We now reduce the power on the a by 1, so it's a to the power 4, but at the same time increase the power on the b by 1, so that's now going to be b to the power 1. Move on to the third term, starts with a 10, and reduce the power of a, so it's a to the power 3, and increase the power on b, so it's b squared now. Next term, another 10, reduce the power on a, so it's a to the power 2, increase the b power, so it's b to the power 3. 2 more terms to go. Next term's going to be 5 from here. It'll be a to the power 1 and b to the power 4. Last term is going to be plus 1, a to the power 0, and then b to the power 5. I could leave it like that, but it's silly really to have the 1 here, so I'm going to take that out. It's also silly to have the 1 here. Okay, so take that out. Anything to the power 0 we know is 1, so that really doesn't need to be in there. So we'll take that one out. And also a to the power 0, that doesn't need to be there, it's just 1. And there is my expansion. I could even drop the powers of b here where it says b to the power 1, just leave that as b, and on a to the power 1 just leave that as a. So that saves us an awful lot of work in trying to expand a plus b to the power 5 with lots and lots of brackets. So I've got another example here for you. This time we're taking it up another level. Expand 2 minus 3x to the power 6. In this example, you've got to take a little bit more care. The a is being replaced with 2, and the b is now being replaced with not 3x but minus 3x, and n is clearly the 6. So you might want to pause the video and have a go at this one, okay? Just give you a moment to do that. When you come back, we'll run through it and you can check your answer with mine. Okay, welcome back then if you had a go. So expanding 2 minus 3x to the power 6, we first of all need to get our values that we're going to be using in the expansion. They won't be 1, 5, 10, 10, 5, 1 because that was for the power 5. We need it now for the power 6. So we just need to put 1s at the ends and add together the 1 and the 5 and the 10 and so on. And if you do that, you should end up with this row here. 1 and 5 making the 6, 5 and 10 making the 15, 10 and 10 the 20, 10 and 5 the 15, 5 and 1 the 6. Okay, so we've got our numbers that we're going to use, and if we put those in, we're going to have the terms like that. We need to think about the 2, the a value. It's going to start with 2 to the power 6 here and then go down to 2 to the 5, 2 to the 4 and so on, all the way down to 2 to the 0. So if you inserted those, you're going to get these terms here. You'll notice I've left out 2 to the power 0 at the end here. Not really needed, okay, purely because it's going to be 1. As for the minus 3x, where we have the b here, it's going to be minus 3x to the power 0 in this term here, but that's going to be 1, so I'll leave it out. Next one will be minus 3x to the power 1, minus 3x to the power 2, and so on. So if you put those values in, you're going to get this result here. So it's just a question of cleaning this up now. So check this out. You should find you get this result here. So not too long by this method, certainly a lot quicker than using the brackets. And so I hope that's given you an idea now on how we can go about using this formula. So in the next section, I'm going to give you a few examples to try, which are going to continue extending this idea. So I'm assuming that you've watched the previous section, and I've got a few questions here then that you might like to try, where you've got to expand the following: 1 minus 4x squared all to the power 4, x minus a half y all to the power 5, and in this one I've included a bracket in front of the expansion of 2 plus x all cubed. We've got 3 minus x all multiplied with 2 plus x all cubed. So you might like to pause the video at this stage and have a go, and then when you come back I'll run through the solutions with you. Okay, so the first thing that we need to do is just write out Pascal's triangle. We're taking it up to the power 5 here, so if you were doing Pascal's triangle, it should look something like this. And also, when we had to expand anything of the form a plus b to the power n, in the previous section, I showed you that we had this formula here. And so for 1 minus 4x squared all to the power 4, using this result here, a is replaced with the 1, b is replaced with the minus 4x squared, and n is the power 4. And that means we're looking at this row here to get the coefficients of each of these terms. And so you should find you get this result. Those coefficients would be a 1, which is really here, okay? We've got the 4, we've got the 6, we've got the 4, and we've also got another 1 there. Then you'll notice that the a value, 1 in this case, goes down in descending powers from 1 to the power 4, 1 cubed, 1 squared, 1 to the power 1. It would be 1 to the power 0, but I've decided to leave that out because it's going to be 1. And for the b, minus 4x squared, that starts to go up in ascending powers. You'll notice I've left out minus 4x squared to the power 0 in the first term because that would be 1. But then I've introduced it here, minus 4x squared to the power 1, minus 4x squared to the power 2, minus 4x squared to the power 3, and finally minus 4x squared to the power 4. If you work this out, simplify it, okay, you should find you get that, okay? So I hope you're able to get that one. For the second example here, the power this time is 5, and you're going to be using this row here. The a is the x and the b is minus a half y. So following what we did in the previous example, you should find you get this result here. You'll notice that I haven't written the ones in Pascal's triangle in the first term and the last term, and I also have not written the minus half y to the power 0 in the first term because that's going to be 1, and x to the power 0 in the last term because that's going to be 1. So it's just a question of tidying this up. Notice too how when we have odd powers we end up with negative terms. Okay, so what we get is this final result. So do spend a moment checking that out if there was any problems. Now we come on to the last example. I picked this one purely because of the 3 minus x being multiplied by the 2 plus x all cubed. We're going to need to just expand 2 plus x all cubed using this row here from Pascal's triangle. So what I'll do then is just write out 3 minus x multiplied by the expansion using Pascal's triangle and this formula here for 2 plus x all cubed. So now if I clean up this bracket here, you should find you get this result here. Next I'm going to multiply through by the 3 and then the minus x, but I'm going to need a little bit more room, so what I'll do is just remove the formula and we get this result here, and then grouping up all the like terms we end up with this simplified answer. So I hope you've been able to get those, and if not, at least being able to see how to tackle them. Now in the next section I want to show you how we can handle expansions where we've got, say, something like this, but it's not to the power 5 but a much higher power, like say 15. We wouldn't want to use Pascal's triangle because it would just take too long. So what I'm going to be showing you next is another formula that we can use that will help speed things up. Now, following on from the previous section, I showed you that if we had to expand a bracket then of the form a plus b to the power m, where m was a positive integer, we got this result here. And where you see these question marks, these coefficients were given by the values in Pascal's triangle. Now there's a problem in using this method when it comes to large values of n. Suppose you had, say, something to the power 15. You're not going to want to keep expanding Pascal's triangle until you get down to the row that gives us the coefficients for the value 15. So what I want to show you in this section is how we can adapt this formula here to cope with large positive integer values of n. So I want to introduce you to this formula here, NCR. Sometimes you'll see other notation used for the equivalent. It could be written like a column vector, nr, or it could be written horizontally. You'll quite often see this on some scientific calculators. Now in this formula you'll see that we've got the exclamation mark here. So what does it mean? Well, we don't call it an exclamation mark, we actually call it the factorial sign. And if I was to write, say, 3 factorial, it represents 3 times 2 times 1. And 4 factorial would mean 4 times 3 times 2 times 1. So you can see we go down in descending integers, multiplying each one. Now most scientific calculators have this function built into them. On this calculator here, it's just to the left of this button here, x to the power minus 1. You can see it written as x factorial. And this is really handy if you've got large factorials to work out. But just to show you, on this one here for 4 factorial, you'd hit 4 and then shift to operate that function, x factorial. Pressing equals shows it's 24. 4 times 3 is 12, 12 twos are 24. So ideal then when it comes to working out large factorials. Now there's one special factorial I want to show you, and that is 0 factorial. And if I type 0 into the calculator here and work out the factorial, you might be thinking, well, is it 0? Well, if I press equals, it turns out to be 1. And we define 0 factorial by definition as being 1. It's not 0. And this is something I'll be demonstrating later on in this section. Now returning to this formula here for NCR, we've got n factorial all divided by the result of n minus r factorial times r factorial. So let me just give you an example of this. Let's say we had to work out 5c2. Using the formula, n is 5, r is 2. So you've got n factorial, 5 factorial on the top here, and then you've got n minus r factorial, 5 take away 2 being the 3 factorial, multiplied with the r factorial, 2 factorial. So if we use the results that I showed you up here for factorials, this is going to expand out to be this result. And working this out, you'll see that it comes to a total of 10. Now it is possible to work out NCR as a function on most scientific calculators. On this one, you'll see the function is just above the division sign here. And of course, if we can use this, it would save us having to manually work out our value by a method similar to this. So I'll show you how we would work 5c2 out on this calculator. Let's clear the screen and we enter 5, and to operate the function NCR, we need to use the shift key, press it, and we end up with C up here. And we need to enter the 2 now, and by pressing equals you get the result 10. So this is a useful function then when it comes to working out NCR values. Now what I want to also show you are a couple of special results, and I'll take these as examples, 3C0 and 4C4. With 3C0, you'll notice that r is 0, so we end up with the r factorial being 0 factorial down here. And in this example, r is 4, and when it comes to n minus r, we end up with 0 factorial in this position. Now, in each of these, the factorials, 3 factorials here cancel out, giving you 1 over 0 factorial. And in this example, the 4 factorials cancel and you end up with 1 over 0 factorial. But 0 factorial is defined as 1. So you end up in both cases with 1 divided by 1, which results in 1. And so they both equal 1. And this throws up this general result that if you have a positive integer n, NC0 is always 1. And also NCN turns out to always be 1. Again, you can check this on your calculator. We'll do just another example. Let's say we do 7C0. So 7C0, just put that in there. Okay, press equals, you end up with 1. And we'll do 8C8 for instance. NCN turns out to be 1. So where am I going with this? Well, if we look at the left-hand side of Pascal's triangle, you can see down this side they're all 1s. And I can pick up on this result, NC0. I can see that we could fill each of these 1s with 0C0, 1C0, 2C0, 3C0 and 4C0 and so on. And when it comes to the right-hand side of 1s in Pascal's triangle, I can fill those in with this result here, 1C1, 2C2, 3C3 and 4C4. They all give us 1. Now when I look at this result here, the 2, it starts off 2C0, ends with 2C2, then what would 2C1 be? Well, we can check that out on here or do it manually. 2C1, just enter that in, press equals, and you see we get 2. That's looking good, so I'm going to put that in there as 2C1. Following this line here, going from 3C0 to 3C3, seems to suggest that this one would be 3C1 and 3C2. And if you did check this out on your calculator, you would find that is true. So when it comes to this fourth line here, if you were dealing with the power 4, then this will be 4C1, 4C2, 4C3 and then 4C4. And so if we put those values in, that's what you've got. Now we knew that in this formula, these question marks were the values in Pascal's triangle. So now we can actually replace them with what we have here shown in blue. So if I put those in, we can remove the question marks, and you can see now that if we've got a plus b to the power n, then those values are given by nc0. And notice, by the way, how I've changed the notation just to save some space here. But it's up to you. You could use obviously this NCR notation, but here we have NC0, NC1, NC2, NC3, all the way up to our last term, which would be NCN. So what I want to show you in the next section is a few examples, which you might like to try as well, where we use this new version of the formula. So I hope you'll have a look at that one. Now, in the previous section of this video, I showed you how we could use a plus b to the power n when n was a positive integer through this formula. It was possibly better than using Pascal's triangle, where we had these combinations nc0, nc1, nc2 and so on. I'm using this notation, or you could use NCR notation, and it was given by this formula here. And this is really useful when it comes to working with high powers, because you don't want to necessarily plough through Pascal's triangle. So I've got an example here: expand all of 3 minus half x, or x upon 2, to the power 10 up to the term in x cubed. So you might want to pause the video at this stage and have a go. When you come back, I'll take you anyway through the work solution. Okay, welcome back then if you had a go. So in this example, the a here is going to be the 3 and b is being replaced with minus x upon 2, and the power n is 10. So using the formula up here, you should have a line something like this. You'll see in each term we've got 10c0, then it's 10c1, 10c2, 10c3 and so on. As for the a value 3, we start with 3 to the power 10 and gradually decrease it by 1 in each term. 3 to the power 9, 3 to the power 8, 3 to the power 7, and so on. And the other term, the b part, minus x upon 2, that starts raised at the power 0, and then it goes up in ascending powers. Minus x upon 2 to the power 1, minus x upon 2 to the power 2, and so on. And notice, by the way, that in any one of these terms, the sum of the powers here, 8 and 2 for example, equals the power here 10. The 9 and the 1 add together to give the power 10. And we'll be using that fact in the next video, where we'll be looking at specific terms in the expansion. Next, we just need to work out each of the values in these terms. As for the NCR notation, should be able to use this formula. If you do work out those values, you should end up with these terms here. So it's just a question now of simplifying each of these terms. If you do that, you'll end up with this line here. Okay, so I hope you're able to see your way through that one and any similar problems. Don't forget to check in the description for links to questions like this that come from exam papers. Now in this next section, what I want to show you is how we handle questions that involve coefficients in the expansion of a plus b to the power n. I've got a couple of examples here, and then in the next section you'll get a chance to do similar examples. Okay, so just familiarize yourself with this formula again. If you're unsure of it, do go back to an earlier section. But remember, this notation here, N0, N1, N2 and so on, often referred to as NCR notation. Just as a quick reminder, writing it as NR, it's equivalent to NCR, which is the function you'll find on your calculator, and it's given by this formula here. N factorial all divided by all of n minus r factorial times r factorial. So in this first question then, find the coefficient of x to the 5 in the expansion of 2 minus 3x all to the power 9. Well, when we're working out a coefficient, I find it's easier to just work with the term first of all. So we're looking at the term in x to the 5. I'm seeing that this will be equivalent to minus 3x all to the power 5 when b is raised to the power 5. And looking at our formula here, we can see that, for instance, if we had the term in b cubed, it would be nc3 at the start. If it was the term in b squared, it would be nc2. So if we're looking for a term in x to the 5 where it's got minus 3x here for the b value, then we're going to be wanting 9c5. Okay, that would be the n value, 9, the power here, and we want the power 5 here on the x term, and it's going to come from the b value, minus 3x, raised to the power 5. Now that means that here we've got to write the value of a, which is going to be 2, but what power do we put to that? Well, do you remember that the sum of these powers here always equals the power n? So therefore we need 5 plus another 4 to bring us up to that 9. So that's the term in x to the power 5. So you can either get on your calculator or work it out manually like this for 9c5, and if you do, that comes to 126, the result of 9 factorial all divided by 4 factorial, 5 factorial. And 2 to the power 4 is 16, and 3 to the power 5 is 243, only it's going to be a negative value because we've got an odd power here. So 126 multiplied by 16 multiplied by negative 243 gives us that x term, and it turns out to be minus 489,800 1,888 x to the power 5. So for the coefficient of x to the 5, well, that's just going to be the value in front of x to the 5 minus 489,888. Well, in the next example, it's following on much the same kind of theme, but this time we've got to find the value of k. We're given this expansion of 4 plus kx all to the power 6, and we're told that the coefficient of x squared is twice the coefficient of x cubed. So we've got to find the value of k given that k doesn't equal 0. So in order to do this, I'm going to look at the x squared term and then the x cubed term, and going to work out what the values are and then take the coefficients of them, form an equation that relates the coefficients of x squared to twice the coefficient of x cubed, and solve for k. So for the x squared term, it's going to have the b value as kx all squared. So I'll just put that in there. It's going to be nc something, n being the 6. We want the squared term, so it's going to be the same as that value there. R is going to be 2. We need the a value, which is 4. And what power do we raise that to? Well, remember the sum of these two powers equals n here, so it's got to be 4 to the power 4. Well, if you do on your calculator 6c2 or do it manually via this formula here, you should find it comes to 15. 4 to the power 4 is 256, and if you multiply that with k squared x squared, then you end up with 3,840 k squared x squared. Now for the x cubed term, then we want kx all cubed, and it's going to come from 6c3 here, the 3 here agreeing with the 3 here. The a part is going to be 4 to the power 3 because those two 3's add together to give the 6. 6c3 turns out to be 20. 4 cubed is 64. 20 times 64 times k cubed x cubed turns out to be a result of 1,280 k cubed x cubed. So we just need to link these coefficients together via this statement here. We know that the coefficient of x squared is twice the coefficient of x cubed, so that means that 3,840 k squared must equal twice 1,280 k cubed. And if you write that equation down, we get this result. We can divide both sides by k squared. That goes out there, just leaving us with k. And so dividing both sides now by 2 times 1,280 gives us a value of k being 1.5 or 3/2. So I hope that's given you some idea then on how to do this type of question. Now in the next section I've got some more examples that you might like to try, so you may want to check those out for further practice. Now here I've got 3 examples that you might like to try as a follow-up exercise to the previous section where we were looking at working with coefficients in a binomial expansion. I would certainly encourage you to have a go at this second question here because there's a slightly tricky bit in it that you've got to take care with. So I'll give you a moment then just to pause the video. When you come back, I'll quickly run through the worked solutions for you so you can check your answers. Okay, welcome back then if you had a go. So in this first one, find the coefficient of x to 4 in the expansion of 5 minus 2x all to the power 7. Well, what we need to do then is, first of all, look at the term in x to the power 4. And so it's going to be the minus 2x, which is going to be raised to the power 4, which is going to give us that term in x to the power 4. And then it's going to come from 7c4, n being the 7, and we want the power 4, okay? And so that leaves us with the 5, which has to be raised to the power 3 in order that the sum of the 3 and the 4 equals the 7 there. And if you work this one out, then you should find 7c4 is 35, 5 cubed is 125, and minus 2x to the power 4 is going to give us positive 16x to the power 4. And tie that all together and you end up with 70,000 x to the power 4. So when it comes to the coefficient then of x to the power 4, it's just going to be the 70,000. Okay? Now I did suggest that you have a go at this one. I've picked it because you've got to take a little bit more care on it. So when it comes to working out the term in x to the 6, well, we've got to look at 5x squared. If we're going to get an x to the power 6, we've got to cube the 5x squared. So when it comes to that term in x to the power 6, we take the 5x squared and cube it. And what that means is that we're going to have n, which is 10, c, and then that power there, 3. And now we've got to take this 3 here and raise that to a power, and we've got the sum of 3 and something gives 10, so it's got to be 7. And so if you work this out, you should find that 10c3 is 120, 3 to the power 7, 2187, and 5x squared all cubed is 125x to the power 6. Put that all together and you've got this very long answer, 32805,000 x to the power 6. I'm not asking for the coefficient of this value, just the term, so that is our final answer. Now for the last one here, we're told that in the expansion then of 2 minus kx all to the power 5, the coefficient of x squared is 4 times the coefficient of x, and we've got to find the value of k given that k doesn't equal 0. And I did a similar example to this in the previous section, so just a bit more practice on this kind of thing. So when we look at that term in x, it's going to be the minus kx all to the power 1 that we have up here. It's got to be 5c1, where the 1's agree here, and that leaves us with the 2 raised to the power 4, so that the 4 and the 1 add up to the 5. And working this one out, you should find that you end up with minus 80kx. Next, I'm going to look at the x squared term, and if you look at the x squared term, it's going to be the minus kx all squared, so it's going to be 5c2, so that those two 2's agree, leaving us with the 2 at the front here being raised to the power 3, such that 3 and 2 make the 5. And work this one out, you should find you end up with 80k squared x squared. So it's just a case now of linking the coefficients of x and x squared through this statement here. We're told that the coefficient of x squared then is 4 times the coefficient of x. So in other words, 80k squared should be equal to 4 times negative 80k. So if you write that down, you've got your equation. And if you divide now both sides by 80k, that's going to leave you with k equaling minus 4. And so hope you're able to get those ones right. And don't forget, if you look in the description, you'll find links to questions like this that you can try for further practice. Now, one of the things you can do with the binomial series is to use it to work out approximations in particular cases. And that is, if x is small, x lying between 0 and 1, then x to the power n gets smaller as n increases. I've got a few examples just to demonstrate that idea. For instance, if you had 0.1 squared, it's 0.01, and you can see that as we raise the power, the value gets a lot smaller. And I've got another example here just with 0.3. When you square it, 0.09, and as you can see, the higher the powers get, the smaller the value. So we can use this idea then when approximating values by ignoring large powers of x. And so what I'll do is I'll demonstrate this with a typical example where we've got to expand all of 1 minus x over 2 to the power 8 in ascending powers of x up to the term in x cubed. And we've got to use the expansion to approximate 0.995 to the power 8 to 5 decimal places. So if we expand 1 minus x upon 2 to the power 8 in the usual way, you should be familiar with this, then working this out, tidying it up, you end up with 1 minus 4x plus 7x squared minus 7x cubed. Now if we're going to use this then to work out 0.995 to the power 8, then clearly we've got the same power here, 8. It just means that 1 minus x upon 2 must be equal to the 0.995, and we should be able to figure out what the value of x would have to be. So if you set up that equation and just rearrange it, you'll find that x upon 2 then equals 0.005, and if you times now by 2, x equals 0.01, a very small value. So as our powers get bigger in this line here, then the terms are going to tend to get smaller, and we should get a good approximation then. So it's just a question of substituting x is 0.01 then into here. Now if you do that, you find that you end up with 0.96069 to 5 decimal places. And when you compare that to what you would get on a calculator if you were to work it out, you can see it's not a bad approximation then to the actual value that you get displayed on a calculator. Okay, so I hope you've been able to get that idea. Now I've got another example coming up that you might like to try, or you can go into the description and there are links there to exam questions that test this idea. Now I'm assuming that you've watched the previous section where I showed you how to approximate values providing x was small in a binomial expansion. And I've got another example here, one that you might like to try. We've got to expand 2 minus x over 5 all to the power 10 in ascending powers of x up to the 4th term. And using that expansion, approximate 1.98 to the power 10 to 2 decimal places. So I'll give you a moment if you'd like to try this, and then when you come back I'll show you the work solution. Okay, welcome back then if you had a go. So let's see how you got on. With this question, it's asking us then to expand in ascending powers of x up to the 4th term. So that means we've got to take it up to the term containing x cubed. So expanding this in the usual way, you should get this result. Now we just need to tidy this up, and if you work that out, you should end up with this line here. Now, when it comes to approximating 1.98 to the power 10, then all I need to do is equate 2 minus x upon 5 to 1.98 and work out what our value of x is. So if you do that, you should find that rearranging this gives you x equaling 0.1, which is a small value. So we should get a pretty reasonable approximation then in the long term. So what I'm going to do then is just substitute this into here, and we will get an approximation then for 1.98 to the power 10, as you can see. Okay. Turns out then to 2 decimal places to be 926.09. How does that compare if you were to do it on your calculator? Well, if you did, it turns out to be 926.0872 and so on. Okay, so you can see to 2 decimal places, it's giving us a reasonable approximation. So I hope that's given you a good understanding now of how to tackle these questions. Now in the next section, I'm going to be looking at working with powers that are not positive integers. Now so far, we've seen that we can expand a plus b to the power n, where n is a positive integer, using this formula here. It's a series of terms and it comes to an end. It's a finite series. But what happens if n is a fraction or a negative value? We certainly can't use this formula then, because these values here are undefined. Is there another way? Well, there is. There's another formula that we can turn to. It's this one here, 1 plus a to the power n, where n is a fraction or a negative value. It's given as 1 plus n times a plus n times n minus 1 over 2 factorial a squared. And you can see the pattern emerging here, I hope. Next term is n times n minus 1 times n minus 2 over 3 factorial times a cubed. If we had another term, it would be n times n minus 1 times n minus 2 times n minus 3 all over 4 factorial times a to the power 4. And this series goes on. It's infinite, never ending. And you'll notice it's only valid for values of a between minus 1 and 1. Or you could write it like this, using this notation: the mod of a is less than 1. Now I'm giving you this formula here and its validity without any proof. All we need to do is to be able to use it. You might also see this in textbooks, not written as 1 plus a to the power n, but 1 plus x to the power n. Obviously the a is being replaced with an x. I prefer to use this version because we'll get expansions where the a will be, say, 3x or minus 2x, say. It can be various functions of x. And I just think having 1 plus x here to the power n makes it a little bit more confusing. So that's the reason why I've gone for using this notation, having an a here. Okay, let's just crack on with an example then. And here's a typical example where we've got to find the first 4 terms in ascending powers of x for 1 all divided by 1 minus x all squared. So how do we do this? Well, first of all, 1 over all of 1 minus x all squared is identical to 1 minus x all to the power minus 2. And so if I was using the formula, let's just say that it's identical to, it's going to be 1 plus n, n being the minus 2, okay, times a being the minus x. So we've got 1 plus n times a, so that's times minus x, and then it's plus, and then we do n again, minus 2, but we now subtract 1 from that value. So it's minus 2 times minus 3. That's all over 2 factorial. And then we've got to multiply that with a all squared. A is the minus x, so we've got to multiply that then with minus x all squared. For the next term, okay, our 4th term and final term, it's going to be n, so that's minus 2 times n minus 1 and times n minus 2. So we just keep taking 1 away from the previous value here. Then that is all divided by 3 factorial and multiplied with a cubed, a being that minus x then, so that's minus x all cubed. And notice that I write plus and so on, okay, on the end, even though we had to write down the first 4 terms. The series continues. I just don't need to put the other terms in. So it's just a question of cleaning this up. And you can check this out. If you clean this up, you should find you end up with this answer. 1 plus 2x plus 3x squared plus 4x cubed plus and so on. Okay? Now in the next section, I'm going to do much the same kind of thing again, but we're going to take it another step further, where we're going to be looking at the validity of our expansion, and there'll also be an approximation that we'll be making, quite a tricky part to the question, so I hope you'll check out that. Now in the previous section I showed you this formula that we could use when n was a fractional value or a negative number for expanding 1 plus a to the power n. Remember, this series was infinite and it was only valid if the a term was between minus 1 and 1. Now what I want to do in this example is just follow that up. We're going to look at expanding the root of 1 plus 4x up to the term in x cubed, state the range of values of x for which it's valid, and in this second part, using x equals 0.01, we've got to make an approximation to the square root of 26 to 4 decimal places. An unusual question, one that certainly I'd encourage you to pay quite a lot of attention to. Anyway, let's start then with expanding the root of 1 plus 4x up to the term in x cubed. Now 1 plus 4x square rooted can be written as 1 plus 4x to the power half, and that's where we start, okay? Now that we've got a fractional power here, that's going to mean we do need to use this formula. N is going to be the half and a will be the 4x. So using this formula here then, we've got to put down all the terms up to the term in x cubed. So doing that, you should get this result here. 1 plus n being a half times the a value, 4x, plus n, which is a half. Take away 1, so that's going to be minus a half over 2 factorial, and then it's the a value, 4x, all squared. Then we do a half times minus half, and we take 1 away from minus a half. That's going to be minus 1/2, or minus 3 over 2. And that's all over 3 factorial, multiplied with a all cubed, 4x all cubed. Okay? So if you simplify this, you should find you get this result here. 1 plus 2x minus 2x squared plus 4x cubed, and so on. So we now have to state the range of values of x for which it is valid. And that's going to be our a value, which is 4x, has to lie between minus 1 and 1. So for this part then, let's just put it in part 1. The expression is valid then when 4x, our a value, lies between minus 1 and 1. And so to find out the range of values for x, I just need to divide each of these sections by 4. And if you do that, you're going to end up with minus a quarter being less than x, being less than 1/4. So x lies between minus a quarter and a quarter. You could leave it like that, or you might prefer to write it in this style. The mod of x is less than a quarter. That's up to you. Now this second part, where we're going to use an approximation, taking x equal to 0.01, we've got to find an approximate value for the root of 26 to 4 decimal places. So This one needs a little bit of pre-work really to appreciate it, because as soon as you put x equals 0.01 into the root of 1 plus 4x, we end up with the square root of 1.04. So let's just start this off by saying that when x is equal to 0.01, okay, we're going to get the square root then of 1.04. The question is, how does this relate to the root of 26? Well, the square root of 1.04 is exactly the same as square rooting all of 104 over 100. So that leads us to cancelling top and bottom by 4. And it's at this point you might start to see 26 coming into this, because 104 divided by 4 is 26 and 100 divided by 4 is 25. And so this is exactly the same as the square root of 26 over the square root of 25. But we know the square root of 25, it's 5. So there's our root 26 there. So what does this tell us then? Well, it follows from here that the square root of 26 must be equal to 5 times the square root then of 1.04. And so all I need to do is substitute x equals 0.01 into here, but multiply our result by 5. And so if you do that, you end up with the root of 26 then is approximately the same as 5 times the result that we get when we substitute 0.01 into here. Work this out then, and what you end up with is 5.09902, which when rounded to 4 decimal places is 5.0990. And that, if you check it out on your calculator, is not a bad approximation to the square root then of 26. So I hope you're getting a feel for this now, but I would encourage you to look at the next example that I give, as it gives another style that we can use this formula in. So here's an example that you might like to try. We've got to expand 4 plus x all over the cube root of 1 minus 2x. Expand it up to the term in x cubed and find the range of values for which the series is valid. So as usual, just give you a few moments to pause the video if you want to have a go, and then when you come back I'll take you through the work solution. Okay, welcome back then if you had a go. Let's take a look at the solution. So first of all then, what I'd want to do is to rewrite the expression here as 4 plus x times all of 4 minus 2x to the power minus a third. So what we need to do next is just expand the 1 minus 2x to the power minus a third, and then we'll multiply it with the 4 plus x. So if you expand 1 minus 2x to the minus third, you end up with this series here. And remember, we're going up to the term in x cubed, so it's going to finish at this point. Next, just going to simplify all the terms here, and if you do that, you're going to end up with this result. I'm going to next multiply through by the 4, and doing that you should have found that you got this result, and then multiply through with the plus x, so you end up with this statement here. You'll notice that I haven't done x times the x cubed term here, because it's going to obviously lead to an x to the power 4 term, and we don't need that, so that particular multiplication was left out. So all I need to do now is just group up like terms, simplify it, and you should end up with this result here. Now, when it comes to working out the validity, then I'm looking at this expansion here, 1 minus 2x to the power minus a third. Remember, it's only valid if the term here in x, minus 2x in this case, lies between minus 1 and 1. So we've got minus 1 must be less than minus 2x, which in turn is less than 1. And what I'd want to do now is divide throughout by minus 2, and doing that gives me minus 1 divided by minus 2, which is 1/2. Remember though that because I'm dividing by a negative number, I need to switch that inequality. So we switch it round. Minus 2x divided by minus 2 just leaves me with x, and 1 divided by minus 2 gives me minus 1/2. But again, I need to switch that inequality round. Okay, so we've got that. And this doesn't look good with your inequalities that way round. We need to have the smallest value on the left, and so if you do that, you're going to have minus 1/2 then is less than x is less than 1/2. You might want to write that as a modulus inequality, in which case it would be the mod x is less than 1/2. Okay, so hopefully you're able to get that one right. If not, at least being able to see how to do it. Now in the next section, what I want to do is go back and look at the validity of expressions, but we'll be looking at extending it a little to simultaneous types. Now in this next section, what I want to do is go back and just extend the work we've done on the validity of a binomial expansion. In this example, I'm going to be looking at what I call a simultaneous type. And so to demonstrate it, I've got this example here. Now if we were going to expand this, I would need to rewrite the 1 plus 3x to the power 4 in the denominator as a negative power, so I end up multiplying it with the 1 minus 5x over 2 all to the power half. Now in each of these expansions, because we've got a fractional power and a negative power, then each of these expansions are going to be valid for a particular set of values of x. So what we have to do then, in order to find the set of values of x which hold for both series expansions, is to choose the smaller of the two ranges. And so when it comes to looking at the first expansion for 1 minus 5x over 2 to the power half, what's it going to be valid for? Well, it will be when this term, minus 5x over 2, then lies between minus 1 and 1. And we need to solve this for x. So I'd multiply first of all then by 2 to each interval there. If you do that, you'll end up with this result. And then I need to divide by minus 5 to each section. And that means turning the inequalities around because we're dividing by a negative number, and then rewriting this going from lower to higher values left to right as minus 2/5 to 2/5. X has to lie between those two values. Now, when it comes to looking at the values of x for which 1 plus 3x to the power minus 4 is valid, then again, what we need is this x term, 3x, to lie between minus 1 and 1. And in this case, for values of x, we just need to divide through by 3. It's a positive value, so we don't need to reverse the inequalities there. So what I can do now is represent these ranges on a number line. We've got minus 2/5 to 2/5 as one particular set of values, so I'll just put minus 2/5 to 2/5 here. And for this range here, minus 1/3 to 1/3, where does that fall in comparison to this interval, minus 2/5 to 2/5? Well, minus 1/3 occurs here roughly. It's greater than minus 2/5, so I'll put that one as minus 1/3, and 1/3 is smaller than 2/5. If you were to change these to 15ths and these to 15ths, you could compare the values and you'll see that minus 1/3 is greater than minus 2/5 and 1/3 is less than 2/5. So the interval we want is the one that is a subset, if you like, contained within the other range, and that's the one that goes from minus 1/3 to 1/3. I can put a little circle around those ends if you like. It's telling me that I am not going to equal those n values. So the final answer then is that this expression is valid for x between minus 1/3 and 1/3. Now so far, when the expansions have been fractional powers or negative powers, we've had to make sure that there was a 1 always at the beginning of the bracket. But this might not be the case in some examples. There could be another value other than a 1 written at the front here. So in the next section, what I'm going to be doing is showing you how we work with questions like that. So do take a look at that if you want help with that type of problem. Now, we've already seen that we can expand 1 plus a to the power n if n is a fractional power or a negative power by this formula here. But what happens if we don't have a 1 in this position? How do we handle problems like that? And to demonstrate that, I've got this example here where we've got 1 all over 2 minus 3x to the power 4. When I rewrite this, you can see we end up with 2 minus 3x to the power minus 4. And instead of having a 1 here, we've now got this 2. So how do we work with this so that we can use this formula here? What we do is we take out the 2 in front of this bracket here and put it all to the power minus 4, like this. You'll notice that we get the 2 times the 1, which is clearly the 2, but we have to divide this term by 2 so that 2 times minus 3x over 2 gives us back that minus 3x. And it's all raised to the power minus 4. And because we've got a product now of 2 values, all to the power minus 4, this is exactly the same as 2 to the power minus 4 times all of the bracket to the power minus 4. And 2 to the minus 4, if we were to rewrite that, that would be 1 over 2 to the power 4. And we can now expand this bracket using our formula up here. And if you do that, you end up with this result. 1 over 2 to the power 4 is 1/16. And if you tidy up the terms inside the bracket, you end up with this result. And then expanding out by 1/16 and simplifying, you end up with this final result here. The aim, though, of this section is just to show you how we can adapt the expression where we don't have a 1 in the bracket here, how we can adapt it so that we end up with a 1 in the bracket and then use the formula to expand it. Now what I've got here are a couple of examples. I'm not expecting you to expand these out, but I just would like to encourage you to have a go at trying to rewrite these where we're able to use this formula here. Reduce these down to an expression that is something multiplied with a bracket that contains 1 plus or 1 minus in to a power. So I'll just give you a few moments to try those 2 examples and then you can check you're working back with mine. Okay, welcome back then. If you had a go, let's see how you got on. Well, being a square root, it's going to be 4 plus 5x all to the power half. But if I pull out 4, then you should have this result here. 4 times all of 1 plus 5x over 4. all to the power half. And then I can use that power on both the 4 and the bracket. So we end up with 4 to the half times that bracket to the power half. And 4 to the power half is the square root of 4, so I can then rewrite that as 2 times this bracket to the power half. And then we would carry on by expanding the bracket and then finally multiplying out by the 2. So what about this one here, 3 all over 5 minus x? How would we handle that one? Well, with this one, we would rewrite it, first of all, as 3 times all of 5 minus x to the power minus 1. Then I'm going to think about pulling 5 out the front of this bracket. And if I do that, you end up with 3 times all of 5 times 1 minus x over 5 to the power minus 1. And then we can rewrite this as 3 times 5 to the power minus 1, all multiplied by 1 minus x over 5 to the minus 1. And we can now rewrite this as 3 times 5 to the power minus 1, and that bracket then all to the power minus 1. 5 to the minus 1 is 1/5, times it with the 3, and you end up with 3/5 times that bracket to the power minus 1. And clearly we would now go on to expand this using the formula up here and then finally multiply by 3/5. Okay, so I hope you're able to see your way through that. And now I've got another example that you might like to try in the next section. Now, just following up what we did in the previous section, that was looking at using the binomial expansion formula when we didn't have a 1 in this position here for rational or negative powers. So if you're unsure about that, do go back and check that previous section out. Anyway, an example for you to try. Express this expression here in the form a plus bx plus cx squared and so on, and state the range of values of x for which the series is valid. So if you'd like to give this a go, I'll just give you a few moments to pause the video. When you come back, then we'll run through the solution. Okay, welcome back then if you had a go. So the first thing we need to do is just to rewrite our expression then as 8 plus 3x all to the power minus a third. So because this doesn't have a 1 in this position, I showed you in the previous section then that we would pull out 8 in front of this bracket and divide the 3 by 8. So you're going to get something like this. And it's all to the power minus a third. Next, we just put each of these values, 8 to the power minus a third and the bracket to the minus a third. And 8 to the minus a third, well, that's going to be 1 over the cube root of 8. So that's going to be a half. And we'll need to multiply that with the expansion of the bracket. And if you could check that out against the formula, you should find you get this. So tidying up the terms inside the bracket, you get this. And now multiplying by a half, you should end up with this line. Next, we need to work out the range of values of x for which the series is valid. And we have to look at the expansion of this bracket here, where it had the form 1 plus a to the power n, a being the 3/8 x, and it's that value that we need to have between minus 1 and 1. So if we write that down, we've got 3x over 8 then lies between minus 1 and 1. We now multiply throughout by 8, and that leaves us with 3x lying between minus 8 and 8. And then divide throughout by 3, and that leaves us with x lying between minus 8 thirds and 8 thirds. And you can also write this in an alternative form as the modulus of x is less than 8 thirds. So, hope you're able to get that correct, and if not, at least able to see how to do it. Now, the next section will be looking at partial fraction types where we take a fraction, split it into partial fractions, and then use the binomial expansion. Now in this section, what I want to show you is how we can use partial fractions to break up a fraction, say something like this, and then go on to use the binomial expansion to then create a series expansion. So I've got an example here, 7 minus 2x then, all divided by 1 plus x times 2 minus x. We're going to split it into partial fractions and then expand up to the term in x squared. So assuming then that you're familiar with partial fractions, what we have here are two linear factors in the denominator, and so that gives rise to partial fractions of the form a constant over one of the linear factors plus another constant over the other linear factor. So we need to find out what these constants a and b are, and to do that we multiply both sides by the denominator here. So doing that gives rise to this statement here. So we next need to make each of these brackets 0 so we can find a and b. So that would be setting x equal to 2, making that bracket 0, and x equal to minus 1, making that bracket 0. So first of all then, when x is 2, we end up with 7 minus 4, which is 3, and we end up here with 3b. And dividing both sides by 3 gives us b is 1. And now setting x to be minus 1 to make this bracket 0, we end up with 7 minus 2, which will give us 9. And here we're going to have 2 minus minus 1, which is 3a. Okay? Dividing both sides by 3 gives us a is 3. So that means that we can now rewrite our expression as a, which was 3 over 1 plus x, and b, which was 1 over 2 minus x. So when it comes to expanding these now, what we're going to do is bring these denominators up to the top and add the two functions together when we've expanded them individually. But before I go on, I can see that this bracket here has a 1 in the front. This one has a 2 here, so I'm going to need to adjust this. So adjusting this in the usual way, we would pull out that 2 in front of the bracket and divide the x by 2. It's all to the power negative 1, and then we can say that's 2 to the power minus 1, all multiplied by that bracket to the power minus 1. Now 2 to the minus 1 is a half, and so I can rewrite this as a half times that bracket to the power minus 1, and we end up with this statement here. So it's just a question now of expanding each of these brackets using the binomial expansion formula. And if you do that, you end up with this quite lengthy line, and then tidying up all the terms in each bracket, multiplying by 3 and also a half respectively, should give you this statement here. And we need to just simplify this, grouping up terms, you end up with this series here. So that's how we can use partial fractions then to help us build up a series through using the binomial expansion formula. Now in the next section, I've got another example for you to try. It goes a bit further as well. It's going to ask you to state the range of values for which the expression is valid for. So that's going to involve simultaneous inequalities. So I'd strongly encourage you to have a go at that one. Now this is a follow-up question for you to try from the previous section where we looked at taking a fraction and expressing it in partial fractions and then going on to expand each term using the binomial expansion. I take this a bit further though in this example by asking you to state the range of values for which the expression is valid for. So just give you a few moments to pause the video, and then as usual when you come back I'll take you through the work solution. Okay, so welcome back if you had a go. Well, the first thing we need to do then is take our expression and write it in partial fractions. So we've got linear factors in the denominator here, so it's going to give rise to this type of partial fractions. Multiply both sides by the denominator, 3 minus 2x, 4 plus x, you should get this line here. And then we need to make each of these brackets 0, so we can make this bracket 0 by taking x is minus 4. Substitute it into our equation here, and you'll end up with minus 11 equals 11b. And that means that b equals minus 1. And to make this bracket 0, we let x equal 3 over 2. And substitute that into our equation up here, and we end up with 11 equals 11 over 2a, making a equal 2. So we can then rewrite our fraction here as a, which was 2 over 3 minus 2x, and b, which was minus 1, as minus 1 all over 4 plus x. Now I need to prepare this for the binomial expansion by bringing each of these denominators up to the top, making the powers negative 1. But when I look at each one of these brackets, they don't start with a 1, and so I need to change them. So when we look at 3 minus 2x all to the power minus 1, pull out that 3 in front of the bracket, giving us 1 minus 2/3 x inside, and it's all raised to the power minus 1. And then that minus 1 goes across the 3 to the power minus 1, and across that bracket, the bracket to the power minus 1. Doing much the same for 4 plus x to the power minus 1 gives you this result here. Okay? Now, with 3 to the minus 1, we know that's a third. And when I multiply it with the 2 here, it's going to be 2/3 times the binomial expansion of 1 minus 2/3 x to the minus 1. And for 4 to the minus 1, well, that's going to be a quarter. So when you write that in, you should find that you've got this result here. So we should be able to now go on and expand each of these brackets in the usual way using our binomial expansion formula for rational powers of n and negative powers of n. So if you do that, you should end up with this result here, which when tidied up turns out to be this line, and then we just group up the terms and we end up with this final result, which I hope you're able to get. Now we need to state the range of values that the expression is valid for, and that means that we need to look at working out the range of values that 1 minus 2/3 x to the power minus 1 is valid for, and 1 plus 1/4 x to the power minus 1 is valid for. And then take the smaller of those two ranges, as I explained in an earlier section. So dealing with this one here, minus 2/3 x has to lie between minus 1 and 1. And if you rearrange that, you should find that for x, it's valid for x being between minus 3 over 2 and 3 over 2. We now come on to 1 plus 1/4 x to the power minus 1. And it's the quarter x that should lie between minus 1 and 1, leading on to that expression being valid for x between minus 4 and 4. So of these two intervals, which is the smallest? It's this one here. It's contained within this interval here. So the final answer then is that our expansion is going to be valid for x between minus 3 upon 2 and 3 upon 2. Okay, so I hope that's been of value to you and you're able to see your way through that question. Well, that brings us now to the end of the binomial expansion, and just want to summarize what we have been through. We saw that if n was a positive integer, then when it came to expanding a plus b all to the power n, it was identical to these terms here and more, which I'll explain in a moment, where we took a, wrote it down as a to the power n, and then it went down in descending powers in each term, all the way down to a to the power 0. And then as for the b term, that started at b to the power 0 and went up in ascending powers for each term, okay, until we got to the last term, b to the power n. There were coefficients in front of these values, and those coefficients, we'll just put some question marks in there, we discovered were given by Pascal's triangle. It was a pattern of numbers where we had ones all the way down this side and ones down this side, and we built it up by adding together two adjacent numbers, and that gave us the number in between, 1 and 1 being 2, 1 and 2 being the 3, 2 and 1 being the 3, and so on. And so these values here replace the question mark. So for instance, if n was to the power 3, we would have had a 1 in here, a 3 in here, a 3 in here, and a 1 on the last term. This would have been our last term. We would have had a to the power 0 b cubed if n had been 3. And we would repeat that for any of these other powers. We then went on to discuss factorial notation. N factorial, as we would say, given by this exclamation mark. It was short for n times n minus 1 times n minus 2, all the way down to 1. So if we have 4 factorial, for instance, it would be 4 times 3 times 2 times 1. And we use this in a particular formula. That formula was often quoted as NCR, and we wrote it in either this notation or this notation. Calculators tend to use this notation, as I explained in one of the sections. And it was equal to n factorial all divided by n minus r factorial, r factorial. And how did this help us? Well, I showed you that if you worked out certain values, 0C0, 1C0, 1C1 and so on, that these values gave us exactly the same values as we had in the respective places here in Pascal's triangle. So what that meant was that we could use this notation in place of these question marks, and it gave us a new formula, this formula here. And so this became a useful formula using the NC0s, NC1s, NC2s instead of just working out the values through Pascal's triangle here. It became more useful when we were dealing with large powers of n or finding a particular term. But then there was a problem. This formula was only true for positive integers. So what I went on to show you was another formula, which was 1 plus a to the power n, where n could be a fraction or a negative value. And if that were the case, we got this result here, that the series was infinite and it was only valid if a was between -1 or 1. And you could use either this notation or the modulus notation. The mod of a was less than 1. Either would do. So I hope that's been of some use to you, and that brings us now to the end of this particular revision guide then on binomial expansion. Don't forget to subscribe so you can keep up to date with any other videos and revision guides that I produce. So that just leaves me to say thanks for watching. See you again, hopefully in another video.